Hi everyone, I'm Harshayu and I'm excited to present LOKI, Long-Term and Key Intentions for Trajectory Prediction. Understanding traffic agents' behavior to predict intent and future trajectories is a critical component for many autonomous systems to plan in the real world. For example, autonomous vehicles, socially compliant robots, as well as delivery bots. Predicting intent and trajectories of other actors can be useful for collision avoidance, path planning, long-term navigation, as well as social intelligence. While there are many publicly available trajectory prediction datasets, only a few have annotations that allow for both intention prediction and trajectory prediction for both vehicles and pedestrians. The PI and JA datasets are publicly available pedestrian datasets that can be used for human trajectory forecasting as well as intention prediction, such as intent to cross or not cross. However, they only consider agents that are pedestrians and reason about current intent for short-term horizon predictions. The STIP dataset has frame-wise intention labels, which does allow for understanding how intent changes over a longer time horizon, but they do not tackle trajectory forecasting and only have pedestrian agents in their dataset. IntentNet, lastly, does consider vehicle agents, but their dataset is not public and they only consider current intentions. To this end, we propose the LOKI dataset. Here is a visualization of the LOKI dataset. As you can see, the Porsche in front currently has a short-term intention, which we define to be 0.8 seconds, of stop at a very busy intersection. However, we see that when the other agents leave the scene, the intention changes to lane change to the left, and the car merges into the left lane. Soon after, the intention changes to drive forward once the car has merged into the lane. Our dataset was collected with both cameras and LiDAR, so predictions can be done with both top-down bird's eye view or egocentric view. More details can be found in our paper. We also have many other labels in addition to intention labels, such as environmental labels and contextual labels. Again, more details are in our paper. Here's a table comparing our dataset to other intention datasets. And as we can see, there are a lot more scenarios, agents, and complex heterogeneous traffic scenes with labels that can be used for trajectory prediction and behavior understanding. So the key idea is that we show that reasoning about long-term goals and short-term intent can play a significant role in trajectory prediction. So given the task of predicting a target vehicle's trajectory, we first estimate long-term goals of the agent, and then we reason about interactions and environmental constraints before finally understanding the agent's short-term intent that will affect the final trajectory. So while our dataset can be used for many different problem formulations, such as long-term, short-term, or using LiDAR only or LiDAR and camera, in this problem formulation, we only use the bird's eye view. So given a past history of an agent, we predict the future positions and intents in the bird's eye view form. The model we propose takes in actors' past information and first estimates a long-term goal independent of other actors. We then have a scene graph and prediction module, which rolls out agent intents and future positions at each time step, while also considering interactions and environmental constraints using a graph network. Future position predictions are conditioned on estimated intents at each time step. We use the standard ADE and FDE metrics, which we define more carefully in our paper, to evaluate the trajectory error performances. Here we present unimodal trajectory prediction performance compared to prior state-of-the-art methods for both pedestrians and vehicles. Hours plus IC corresponds to results with intention conditioning, and hours plus IC plus SG is our full model with a scene graph to share information between agents and consider environmental information. We observe that there's up to an 8% improvement in performance when reasoning about intent. We also observe a similar performance boost in the multimodal setting. Here, the number of samples is 20. Here are some graphs showing the results of intention prediction performance across the 5-second prediction horizon. We see how there are various patterns for different intention types and see how the accuracies are better with multimodal predictions. Our dataset is annotated at a much higher FPS than other intention datasets, and to evaluate how this would have changed with a lower FPS annotation rate, we see how behaviors such as turning and lane changing, it is crucial to have frame-wise intention labels at a higher FPS, and for pedestrians, the performance is not as apparent. Lastly, we visualize some top 1 trajectory prediction performance visualizations, as we see here. And finally, we also have some multimodal predictions, which we roll out using our model. Thank you so much for watching, and for more details, please refer to our paper or visit our dataset webpage.